In this video, I want to cover an example involving a decision analysis technique. Let's go ahead and look at the following problem. Blackbeard's Phantom Fireworks is considering introducing 2 new bottle rockets. The company can add both to its current line, neither, or just one or the other to their current product line. The success of these products depends on the consumer's reactions. We have estimated the probability of 3 what we would call states of nature, 3 reactions that we expect, and that is summarized by the following. We expect there to be a 30% likelihood that the customers will act in a good manner. We estimate that 50% is likely to occur with a fair reaction, and finally 20% chance that the consumers will react poorly. The company's revenues in thousands of dollars are estimated in the following table. Let's just talk about this table briefly. We have the payoff table, which is summarized here in terms of what the company expects if one of these states of nature occur. So, for example, we have a decision to make, and that is going to be neither product 1, product 2 only, or both. And the probability of these states of natures are actually documented here as well. So 30% chance it'll be a good reaction, 50 fair, 20 poor. The payoffs are these values. So if we didn't do anything, if we made a decision not to launch either into our product line, we would have a revenue stream of $0. If we would decide only to launch one of the 2 bottle rockets, we expect to make $125,000 in revenue. Product 2, if we just do product 2 only, we'd expect that to be $105,000, and if we did both, $220,000. Okay, so we rate the same things in terms of fair and poor. So this is our payoff table with the states of nature defined. So what about decision-making techniques? What do we have available to us? Well, they're all listed here, A through G. We have a strategy called Maxi-Min. This particular strategy is a pessimistic strategy. So we take all of the likely outcomes and take the minimum payoff of those outcomes in terms of the decision and take the maximum of the minimum. Likewise, we have a very optimistic strategy where we essentially take the best of the best. We also have a more realistic approach where it's the expected monetary value. And then we have another decision technique called Minimax Regret, which requires calculating a regret table. Finally, we have a computation that we can compute the expected opportunity loss. And finally, the expected value of perfect information. So all of these can be used in conjunction when making a decision. And in this particular problem, the decision is whether we should launch neither, only product 1, only product 2, or both simultaneously. And we're going to use these techniques to determine what we should do under these strategies. So let's go ahead and open up the starting file. Okay, we have the payoff table in our Excel spreadsheet here. Let's first determine the Maxi-Min strategy. And for all of these, I have a very particular way I calculate these to try to maximize the functionality of a spreadsheet. So let's go ahead and begin this process. What we're going to list here in terms of the strategies that we're going to solve for. The first one, which will be on the same row as the states of nature. So let's go ahead and place the title Maxi-Min. Then next, Maxi-Max. And then the expected monetary value. Okay, I'm going to bring over some formatting. And hopefully once we're finished with this, everything is formatted well. Oops, I didn't mean that fill. Let's go ahead and do that again. Okay, so let's work on each one of these separately, and then I think you'll understand the layout of what I'm doing here. the first thing we've got to do is understand the approach of the maxi-min. The first thing we need to do is actually calculate a min based on the payoff table. So just for notes, I'm going to go ahead and write min, and it seems I've got this formatted as white text. Let's go ahead and change that. Okay, so the first thing we need to do, and if you want to write notes, this is the first step. We need to take a min. And what I recommend to my students is that we look at these solving techniques backwards. Meaning, if we're talking about a maxi min, the first thing we want to do is find the min off of these values in the payoff table. And then later, we're actually going to look for the max. So step 1, read the word backwards. Find the min. Then step 2, find the max. So I'm documenting min here. Let's just go ahead and calculate the min based on these 3 values. So if our decision was neither, the min, of course, of 0, 0, 0 is going to be 0. Let's fill this formula down. If we were to launch product 1 only, the minimum payoff as a result of either one of these states of nature, which again is not certain, but we place probabilities on these happening. The minimum actually is a 30, which would relate to the poor. Likewise, if we just launched product 2, we would also have a 30. So that's the minimum, and then finally 40. So right now you can see we're being very pessimistic as far as the values obtained from this payoff table. It would be nice, of course, to get the maximum, but that's actually the next strategy, the maxi max. But with that, of course, comes risk. So the first step, find the min, and we've done that. Next step, we're going to find the max, and I'm going to copy some format here. We're going to calculate the maximum for the maxi min. So again, I told you calculate the min first, then the max. So we've got the min. Let's go ahead and calculate the max now. The max would actually be the maximum of these 4 minimums. So that's why this technique is called maxi min. Find the min, find the max. Okay, so what about the next one? Well, first, let's not let this pass us by here. So what does this actually mean? What does this 40 actually mean? It's telling us essentially that the best decision to make with a maxi-min strategy, which is also pessimistic, is to take the option with a 40. So that would mean that we are to make a decision to launch both. And let's go ahead and document this. The decision, and we're going to utilize some good old Excel functions here. Let's identify the decision. How about with an index match? Okay, so the index, we want to return one of these 4 outcomes, neither product 1, product 2, or both. Now, I want to find the row number that corresponds with this 40. So I'm going to use a match and look up the 40 here in the max and look where this 40 lies within these 4 values. Okay, I want to match type 0, and I'm going to end that with a parenthesis, and this is always going to be in column 1. Now my intent is to fill this to the right, so I'm going to go ahead and lock the columns of this range so it doesn't move across. The other ones are okay, they can all move across. So what this is essentially telling us is that we have both. That is our decision. Our decision is to launch both into the product line. Okay, how about the next one? Let me just format these while I'm thinking about it. Let's start with calculating the max. So this is going to be an optimistic strategy. So if you actually want to document this somewhere, we can put pessimistic, optimistic, and this is our realistic strategies here. Okay, so moving on to maxi max, let's find the max first. The maximum will be calculated of the 3 states of nature for this decision outcome, neither, which of course is 0. Let's fill this formula down. And now we're ready to calculate the maximum of the maximums. So let's try to identify that. Max of these four values is 220. 220 relates to the decision of both again. So it seems so far that regardless of the pessimistic or the optimistic strategy, the data is telling us that we are better off actually choosing to enter both product lines. What about the realistic approach? Now, be careful or be aware that each one of these strategies can definitely result different decisions. It just so happens that the pessimistic and optimistic in this particular example is the same. In terms of the realistic probability or outcome of this payoff, we're actually going to calculate that with a sum product. And we need to calculate the expected value of each one of these payoffs in regard to the probabilities of the states of nature and the payoff. So that's going to be a sum product of the probabilities. We can lock those in, comma, and then the individual payoffs. Of course, for this one, it's going to be equal to 0. No surprise. But what about the next one? The next one has an expected payoff of 76 based on the calculation of 30% times 125, 50% times 65, and 20% times 30. Okay, so let's fill this down to the remaining cells. And what we need to do here is actually calculate the maximum of those expected values. So we can fill that formula. The maximum happens to be 129, which does relate to the both. So far, any decision-making strategy that we've implemented are all pointing to the both. Now let's look at a couple others. More or less looking at, well, if we take in regret into the equation. Regret is essentially the difference of the best possible outcome and a current decision outcome that could be made. So if I said, well, I have money rolled up in my hands, and I say pick the left or the right hand, and you picked the left hand, and there was a $50 bill in there, you'd probably be happy to take that. But the other thing is, you don't know what's in the right hand. Well, later, I would open up my right hand and say, here's a $100 bill. You could have had that. So actually, your regret on this decision is $50. It's a difference between the max, which would be 100, and the decision outcome that we selected. So this next portion of this problem-solving technique is identifying a regret table. So let's go ahead and do that. And to do that, what I'm going to do is actually copy this table verbatim. Just copy it, and I'm going to paste it right here. And instead of this being a payoff table, it is now a regret table. We still have our states of nature, we still have the same probabilities, but we're going to calculate our regret. So let's go ahead and remove that. Okay, so how would we calculate the regret of the good state or nature? So the best outcome that we could have had if the state of nature lands on, if you will, occurs or happens to be good, is the maximum value here. Well, the maximum value here is 220. So what we could actually do is embed that calculation, or we could actually just calculate this field by itself, which actually might come in handy later. So what I'm going to do here is just calculate the max. And let's go ahead and use some formatting. So what I'm going to do is calculate the max of these four values and fill that over to the right. Okay, so if I happen to make the decision that it's neither, I'm not going to do anything, I'm not going to add either one to the line, I would have a regret value of 220, and let's lock the appropriate row here, not the column. It would be a regret of 220 minus 0. So essentially, if I decided to do neither, my payoff would have been 0, and I would have had an opportunity loss, a regret of not making $220,000. What about the next one? I have a product one only decision that would have yielded me $125,000, but looking back at hindsight, I could have made 220. So the regret here is 220 minus 125. Let's calculate the rest. I have a regret here of 115, so 220 minus 105, and then I have a regret of 0. We definitely expect this because if we happen to choose both, and both is the best option in terms of the max, then the difference there is 0. Let's fill these to the right. You can double check the calculations there. Always a good idea to do so to make sure you're calculating these correctly. Okay, so based on this regret table, we actually have a few more decision-making categories that we can invoke. So what we're going to do down here is very similar to this table. I'm going to just copy this and paste it here, and I'm just going to paste the formats. And we're going to have a very similar table. Now, what we can do, I don't like cells touching when they're not logically related. I'm going to insert a column here and just delete the contents of those columns. So now our work is separated out a little bit. What we could have also done perhaps is move this table up here to where it's a little bit better aligned. More logical flow. So we have the max from the table above, and then to calculate the regret, it requires both of the values above. So I think I like this layout a little bit better. You just have to be aware of what all these maximums and things like that are associated with. Okay, we're still going to move down here, and we have the decision-making title of Minimax Regret. Okay, Minimax Regret. So we're minimizing our regret, which is a pessimistic outlook. Okay, so what do we need there? We need to find the maximum. So again, you can read these titles backwards. The first thing we needed was to calculate the regret table. We've done that here. The next thing we need to do is to find the max, and then finally the min. So we can go ahead and type min down here and the decision outcome here. The maximum of these three columns is going to be 220. So these all represent the regret. The maximum regret is 220, but let's take the minimum of those maximums. And the min here is going to be 0. And let's see if we can copy this formula down. I'm not sure if we can. Looks good. We're looking up the value here in this range, and it's reflecting this decision. So in this Minimax Regret, we have a decision that is the same as the ones above. This doesn't necessarily have to happen like this. This is somewhat of a rare case where they all so far are agreeing. Let's look at the next one. I'm just going to copy this, paste special formats, and go ahead and work on the next one. The expected opportunity loss. Okay, we'll also need a sum product here. So this is more of a realistic approach, because we're involving the probabilities of those unknown states. So here we would have a similar calculation, sum product, the probabilities, we can lock those, and sum product that with the payoffs per the decision. So here what we have is an expected opportunity loss of 129, 53, 61.5, and 0. Okay, here we're actually taking the min as well, which is exactly why I arranged the problem in these steps. We have the maxi-min, maxi-max, expected monetary value, and those all require a maximum. Here, these two decision-making strategies require the minimum. So that's exactly why I arranged it in this fashion. Okay, let's move on to the next calculation. We have the expected value given perfect information and the expected value of perfect information. So a little bit different there in terms of what that actually means. Let's go ahead and document those strategies here. I'm going to copy this. I'm actually just going to copy the headers here. We have expected value given, and I'm going to write that with a this symbol here, the given symbol. It's right above your enter key if you hit shift. Expected value given perfect information, and then we have expected value of perfect information. So a very subtle difference there. So in terms of this first one, the expected value given that we have perfect information. If we had perfect information, it means we could make the best decision if we know the states. So this will actually be calculated with a sum product. And this value represents sum product of the probabilities of the states, comma, and then the maximum. So that is where we have the perfect information. We have the maximum of each state of nature. Now we're just calculating the expected value based on the probabilities given. So here we have an expected value given that we have perfect information, that we have the best in regards of each state of 129. Okay, what does that mean? Well, let's wait and hold that discussion until we calculate the expected value of perfect information. So to calculate this, it's actually going to be a difference. The difference is going to be between the expected value given perfect information minus the realistic maximum here of 129. So it's saying that we have 0, and that's okay. What this is essentially telling us is, are we willing to perhaps pay maybe a consultant for extra information regarding these payouts and redefining these probabilities? So maybe if we spent some more money and some time on this, we would have a consultant make sure that this is 30, 50, and 20. Maybe it's more like 20, 40, and so forth. And so anyway, what this value tells us, this comparison, is that the difference is actually 0. So we can feel pretty good about this decision. If the value is really high, then there's some doubt in our decision-making ability. So what I want to point out is that there are some notes available for this decision-making approaches. So the elements of a decision, we have the available choices. In this case, we have neither product 1, product 2, or both. We have the states of nature, which are usually not under the control of a decision maker. We don't know, for example, how the consumers will react. Then we have the payoffs. So in this particular problem, we have payoffs. It's likely we could have other tables, payoffs, or perhaps cost and things like that. So we have a breakdown of the statements that we need to consider, and this is where I was talking about having a payoff, break even, or potentially a loss. I have definitions here of the expected monetary value, which is that sum product formula, the opportunity loss formulas, the expected opportunity loss, the Minimax Regret strategies. Again, this is where just pointing out that Minimax strategy maximizes the minimum gain, so it's a pessimistic strategy. The Max strategy maximizes the maximum gain, so it's the opposite, so it's therefore optimistic strategy. Minimax Regret minimizes the maximum regret or the opportunity loss, which is another pessimistic strategy. Now here I have some information regarding the perfect information, which is a little challenging to overcome what it actually means. So what is the worth of information known in advance before a strategy is implemented? So that's where I was referring to. Is it worth us spending more money making sure we've got the information at hand to make that good decision? The expected value of perfect information, the EVPI, not the given perfect information with the line in between, is the difference between the expected payoff and the state of nature where known and the optimal decision under the conditions of uncertainty. So here's the steps. Compute the expected value of uncertainty, compute the expected value of uncertainty, subtract the two. So that's exactly what we have done. Where the expected value under the conditions of certainty, we've said that given that we had perfect information, meaning the best decision was made underneath each state of nature, if we can calculate that, and that's what I'm referring to as that EV given PI value, we simply subtract that from our expected monetary value from the first set of rules that we implemented.